Okay, thank you very much. I'm sorry again also for not being there. I also had similar problems with visa and passport expiring, but which was an unlucky combination. But I would like also to thank even more the organizers for also giving me the opportunity to present my research online. And I would like to spend this time to tell you a little bit about what is my research in studying how data-driven machine learning models, generative models can be used to generate turbulent flow, and in particular also to reconstruct flows with a geophysical interest. To give a quick example of the problems I have in mind, I like to show this cartoon that is here on the left, where I put a satellite that is observing the ocean dynamics, and at some point there is some problems. There is a cloud, for example, and we have a loss of some information of the ocean state, and we would like so to find some ways to infer or to reconstruct the missing information. So this is a little bit what I'm going to talk about. And first of all, I would like to start also being a little bit more quantitative, explaining why we need indeed to reconstruct missing information when observing complex systems, like, for example, the ocean dynamics. And to do that in a more quantitative way, what we can do is looking at the energy distribution of the energy spectrum, which is so of the ocean surface current. And this is telling us how much energy is distributed as a function of the different size of the structures that are evolving in the ocean currents. So we can see that actually this covers a very wide range of scales that goes from planetary up to the very small scales. Actually, these small scales, which here are around 100 to 10 kilometers of size, is not the smallest scales in the system. This is actually only the scales we can observe with satellites or the scales we are able to reproduce with numerical simulation. But indeed, the ocean has a dynamics that is much more rich. And indeed, if we go to the smaller scales, the problem is even more important, because it's even more complex, because in some sense we open the third dimension. So the three-dimensional structure of the ocean becomes even more important, and we enter in a field which is not, because it's small at smaller scales, not simpler. Actually, it's still very, very complicated, and also from a theoretical physics point of view, is a very important open problem that is is considered the three-dimensional turbulence, the last problem of classical mechanics that is still unsolved. So, of course, there is a lot more that we should know about this kind of systems, and a lot of information we would like to infer and to be able to reconstruct. So another thing that I would like to stress is that when speaking about reconstruction, indeed, the reconstruction is a big word that can be divided again in many different branches. So we have, for example, reconstruction of a full state, when we imagine to observe only partially the state of the system and we want to reconstruct, infer what is missing. We can have inverse problems reconstructions. As I said before, we observe the ocean on the surface, and at some point we would like to understand its three-dimensional structures. So we would like to understand what happens in the deep ocean. Or we can measure temperature, and we would like to infer velocity. So we can solve this kind of inverse problems. There is the problem of, which is connected, the problem of reconstructing in Fourier space, which is, in the terminology I've used, is a sort of super resolution in real space. So we would like to infer what happens at small scales, looking only at a coarse field dynamics. This is also very connected with the problem of modeling, because modeling means reconstructing what the small scales should do on the large scales that we are actually resolving. So there are a lot of questions that one can ask when dealing with the reconstruction of complex systems. And in particular, to make things simple, I would like to specify one particular point in this talk. I would like, as I said in the beginning, imagine to reconstruct some partial information that are missing on the real state of the ocean. For example, we have a cloud, or we have a gap in our observation. There are different ways people are studying, in the data simulation, people are working on these problems since decades. And one possible way is the one of using equations. For example, you solve numerically the equation of your system, imposing some sort of boundary conditions given by the observations. This is a possible way which has some limitation because as the limitation that we need to be able to perform numerical simulation of the original system. And can be a problem that is in general non-trivial. So the question that we are trying to investigate now that there are new tools coming from computer vision, like for example, these generative methods that people are using to reconstruct damaged images, only having some training data set, we are trying to understand if the same tools can be indeed used to reconstruct solutions which are statistically consistent without knowing anything about the equation of motion. So we would like to have data-driven models that can solve the same questions we are also able to solve using physical systems, physical models. To study this problem, my approach is the one of building up a numerical dataset of complex systems that are complex but a little bit more idealized than the real ocean. For example, I consider a cube of three-dimensional fluid, which is evolving with periodic boundary condition, which is non-homogeneous, maybe non-isotropic as turbulent, as real ocean, but it has much simpler boundary conditions. And I build up a large dataset that I can use to actually validate the different methods. So having a ground truth is very important at this stage because it gives us the possibility to actually give a precise uncertainty quantification of the different methods and to have a fair comparisons of these data-driven approaches. So I build up this data set, I build up also my own damage, my own gap, and I try then to reconstruct it using different approaches. Data-driven approaches also are not only machine learning-based approaches. There are approaches that are linear, for example, as the famous examples of empirical orthogonal functions that here I called proper orthogonal decomposition, but this is exactly the same, which aims to reconstruct the solution on the base of a linear decomposition of your field. And at the same time, I'm trying to understand and investigate how the newer, if you want, nonlinear methods from computer vision can indeed try to solve the same problems and what are the advantages that they might bring. The example I want to give you is what I think it is now the state of the art in generative models, both in physics and in computer science, that are diffusion models. Diffusion models are very recent, and the approach here, the difference if you have a little bit of experience with the other methods like generative adversarial networks, GANs, the difference is that the generation, if you want, and then I will consider also how we can also reconstruct, but in principle, let's start also considering the simple problem of generating data. The generation does not happen in one step. So there is not an input that is given to a network that is outputting a sample of our data, but the generation is embedded inside the process that is called this diffusion process, that starting from some input that is purely random, aims to generate a sample that can belong to our training dataset. So this is an example that has been derived, that has been proposed in the context of computer visions, and the same thing we are trying to do to generate these two-dimensional snapshots of turbulent flows. Diffusion models are technical. I don't want to give you the technicalities because also it would be impossible in a very short time, but I would like to give you quickly what is the physical hint that there is behind this approach. And this approach is indeed strongly based on theories that are coming from statistical mechanics and stochastic processes. And the idea is the following. So we can imagine to have a training dataset. Of course, we need to have a training dataset if we want to train our network, as in all cases. And we imagine that this training dataset is made of different samples. We have that is here called A. We have several samples. We have P, where P can be very large. And A is a field that lives on a very large dimensional space. For example, is an image, and N is the number of pixels of each that are inside each of the images. Then there is, if we have the training dataset, we can do another thing, which is still not, if you want, this is required to build up the diffusion model, and that is what is called the forward process, which is defined in terms of a Langevin equation, where we imagine to start at time 0, taking one of our sample in our training dataset, and then we imagine to evolve it adding this through this Langevin equation, which consists in adding slightly, step by step, some Gaussian noise that is completely uncorrelated in space and time. So we take in input one of our images, which is a dog in this case, and we gradually add noise on top of it until at the end of this very long process, we arrive into a sample that can be completely taken out of one Gaussian that is completely standard and each pixel independent on the other. So this is the forward process. And about the forward process, we can know everything, more or less. Also, the probability of each to observe any of these samples during the forward process, which is given by the probability of taking one image from out of our training set, plus the merging of these multiple Gaussian that have been used to add noise on top of our system. Of course, this is completely determined apart from the fact that the initial data distribution is unknown, because in general, we don't know what is the distribution probability of our training dataset. So now it comes the goal of the diffusion models. The diffusion models aims indeed to define a backward Langevin equation, which is inverting the forward process. So we want to start from Gaussian noise and invert the dynamics, such as at the end of the process, we are able to generate a possible sample that could be extracted out of our distribution of the training set. There is a mathematical result, a theorem that tells us that the inverse equation can be written in this way, which is again a Langevin dynamics, but it is damped by a term, which is the score term. So understanding what is this term, what this term should be in our process is the goal of the diffusion models. So in principle, we want to learn what is the drifting term that starting this backward process from pure noise ends up into the distribution of our training dataset. This function can be written as the gradient of the logarithm of the probability of our dataset at all steps, which is, again, as I said, unknown, because in principle, we don't know what is the initial distribution of our dataset, but this could be approximated by a neural network. So this is if you want, the key idea behind the diffusion models. Now, let's try to go straight to the results and see how these models indeed perform. And to do that, I'm showing this first result that we got in generating Lagrangian trajectories of particles advected by turbulent flows. So imagine we want to generate drifters that are advected by the ocean surface currents, and we want to generate synthetically this kind of data. What we have shown here is that diffusion models indeed perform in a way that I would say is surprising, in the sense that all the observables, statistical observables, like for example, the probability distribution function of velocity increments at different, taking two velocity at a distance that depends on tau for very different taus, we see that actually the models are always able to generate data that are indistinguishable from the statistics of the original dataset. Here, the original dataset is the black line. The circles in blue are instead the data generated by diffusion models. This was very surprising, and more details are discussed in this paper that has recently come out in Nature Machine Intelligence. And now I would like to, motivated of this positive experience, of these positive results that we got, we tried indeed to generate data out of two-dimensional snapshot of turbulent flows. So the idea is now here that we want to follow this backward process that, starting from pure noise, gradually denoise the image up to generate something that is completely indistinguishable from a real turbulent flow. And so this backward process is defined on top of this backward transition probability, which, given in input an image which is a little bit more noisy, it tries through a very complicated and deep neural network to give us in output what is the most probable next step that we should follow in this backward chain. As I said, this is a purely generative algorithm. We wanted to do reconstruction, but reconstruction is a very straightforward step that we can take once we are able to generate, because it's just a conditioned generation. So we want to generate data on top, conditioning on some observation. So we want, again, to define the backward process that generates the missing region starting from random noise, But on top of the random noise, we also have the extra information coming from the frame, so from the region that we have been able to observe. So the neural network now will give us in output this denoised, gradually denoised version of our reconstructed field, always having the extra information on the support of the observations. So this is the idea. This was the approach. Now I would like to share with you a couple of results to give you the feeling of when these kind of algorithms can be indeed important. And I would start showing when actually they do not perform better than the standard linear methods. And to do that, I start from from comparing the diffusion models with a linear classic method, like proper orthogonal decomposition, on an evaluation based on the mean squared error between the original data, so the ground truth, and the proposed reconstruction. So if you see the mean squared error for the two different methods is actually indistinguishable for all the size of the possible gaps that we have investigated in this problem. But of course, this is not the end of the story, because if you look at one specific example of the reconstructed images, you see that the linear POD are much smoother than the diffusion models. And indeed, they look very much not realistic compared with the original fields, while the diffusion models are actually indistinguishable from the real data. We can be more quantitative on estimating indeed to actually quantify this statement, and to do that, I'm showing here what are some statistical comparison of the reconstructed data with respect to the ground truth, so the DNS, which is again here the black line. And you see that for the different observables, diffusion models, this is the PDF of the velocity already, is always indistinguishable from the ground truth. And while POD are a little bit different, you see the differences becomes even more important when we look at the statistics of observables that are more complex, where we have Gaussian, we have less Gaussianity, so we have the formation of these fat tails, and we see that the POD are strongly affected by their approximations, while diffusion models are always indistinguishable from the ground truth. This difference can be indeed quantified, so the distance between these two distribution probability can be measured by measuring the Kullback-Leibler divergence, and we see that in this case, while for the mean squared error the two methods were the same, in this case we have the improvement given by the diffusion model that can be as large as 1 order of magnitude. And this is also some of the results we have presented in this work. So diffusion models, data-driven methods, strongly nonlinear, can be useful if, in particular, we want not only to have a reconstruction that is, let's say, well approximated in terms of a local point-wise reconstruction, so the mean squared error reconstruction, but we want to have an approximation that is as accurate as possible to match that particular boundary condition, but also always statistically consistent with the physics of the real system. So what is the state of the art? These are all, anyway, I think, from my opinion, results that are proof of concepts, that are benchmarked on very idealized setups. I think it is important, and there is still work to be done, to understand how these approaches can be extended to state-of-the-art datasets as the one that I started from, of the real ocean dynamics. And there are several problems to do that. Some of them are technical, are really how to perform this numerical computation, and also there are questions that are more theoretical, that are connected with the stability of these approaches and the generalizability of those methods. And so this is the line of research that I am pursuing. And before concluding, I just want to advertise that because I think there is still a lot to do, we are also trying to set up an open science strategy where all the results, all the data, all the codes that we develop, we try to make available online on the dataset, that we invite everyone that is interested to go, to use, to explore, to repeat our work, and also maybe to improve testing different algorithms. And with this, I stop. Thank you.
Thank you, Michele. I have a question.
Yeah.
Can I just ask it first? So, can you apply this, all the examples that you showed were reconstructions in spatial space?
Mm-hmm.
You could also do this in spectral space. presumably.
Yeah. If I mean, generally, you can do as long as you have a training data set. So you need to have data that are, you need to have to be able to observe your system. So if you want to reconstruct a gap, you also need to imagine that at some point you have some data that are not that are gap free, or you need to reconstruct to constrain that you need to build up a data set in that way. That can be also in Fourier space. The choice of the base is completely arbitrary and depends on the specific goal. So it's on the it's depends on the experience of the person that is solving the problem. If you think the Fourier space is a better base, then you can go with it.